In today's video, I'm going to teach you how to solve this. And what is it? One of the most searched for problems when we're talking about working with Precast. It is how to find the center of gravity of a wall which is going to be placed in a Precast building. Why do we even need that? Well, perhaps just to be able to hold it and place it in their correct position. Of course, we are going to be seeing how this is done programmatically, automating with Dynamo. Okay, so first step is to draw a schema. If you start working with me, if you start studying with me, either in the Dynamo Bootcamp or in the Dynamo Python Mastery, you will see that I'm always drawing this. Why is that? Because no artificial intelligence is going to teach you how to think. So you actually have to do something about that. You actually have to go and find your step-by-step process. So the first step will be to select the walls. This step is a difficult step. Why is that? Because this depends completely on the user. So even though the user has to select this, I'm going to try to make sure that this is as simple as possible and that the user can select other categories. Okay, so only this, careful. Then, as with the wall selection, we might encounter some problems, as for instance, is selecting curtain walls. So we have to use a filter. So we will use our filter and remove those that are curtain walls. Okay, so these ones we are going to completely omit. Then we are going to be left with the normal walls. And now from these ones we are going to be needing two things. First we need their volume and we need their centroid as well. Why is that? Because on the very last step we are going to be using the compound centroid formula in order to get the center of gravity of the walls, even when they have gaps, even when they have windows or doors in them. So we need their volume and we need their centroid, and this would be good enough for which walls? For those that do not have any hosted element, that do not have windows, that do not have doors. So this would be okay for those that don't have any hosted elements. So we have to split up these walls, and when I say split, I mean to divide them, to simply separate them in two groups. So group 1 would be those with no hosted elements. Why is that? Because, well, for those with no hosted elements, their centroid is already the center of gravity, so good for them. We wouldn't be needing anything else here. But we have a secondary group, which is with hosted elements. Now this here is where this script can go funny. Why is that? Because some walls may have one hosted element, like a window, but others may have more, several of them. So we have to consider which wall really has inside each window, each door, and consider them together. Why? Because the formula of the compound centroid has to take into account everything. So from those hosted elements, we need to get centroid and volume. But never lose sight of where do they come from, which is their corresponding wall. So do take that into account. Once all of this is clear, we do with this and with that, we work with the compound centroid formula, which we'll be using to find the center of gravity. Now that you have everything clear, now that you know what we are going to do, you may want to take a picture of this, snap this, so that you may follow me along the video and you know what I'm actually doing, not just watching notes as they go by, as if they were sheep. Okay? There you go. Okay, so after we got our step-by-step process, the next step is to head straight for Dynamo. And here, our first step was to select the walls. So let's pick select model, and here I have several options. Let's write here elements, but I don't want any option, because if I were to pick this, for instance, select model elements, then I will have to add a filter so that we only take into account the walls. So what am I going to do? I'm going to pick this other option. You may not see this if you open your own Dynamo, the Archilab, because this is a package, but you will certainly be seeing select model elements, and select model elements by category, at least if you have version 2025, which is what I have here open. So in this one, you have to pick the category right below that we pick the walls, and here you can click select, and then we do it like this. We go over everything we want to select from the model, and then we click finish. And if I click run, here I have all the walls. Now the second step was to filter, and in order to do that we have to remove the curtain walls. So we are going to first go for the element type. And why are we going to go for the element type? Because whether this is a curtain wall or this is another kind of wall, this information is stored inside the element type. So let's go straight for that. And here we have the wall types. And if I go for element name, here I have the names of these wall types. Some of them do contain the term curtain, others don't. So I want to remove those that contain curtain within its type. So here I'm getting the name of the type. By the way, this is something I hadn't mentioned before, but I'm not doing this Dynamo out of the goodness of my heart. I published something on LinkedIn, and the Spanish community, the ones from the Spanish equivalent of this channel, did respond a lot. However, the English version, that was only crickets. But those people that responded are going to be getting this Dynamo, so if you don't want to miss out on these opportunities, I suggest that you follow me on LinkedIn, and I'm going to leave you here a QR code so that you can go to the LinkedIn page. On with the Dynamo, so we have to filter those that contain curtain within its names. So let's go for string contains. String is the way in which programmers call texts. So we are looking into this parameter, which is the name of the type, and we want to see whether this one contains curtain within it, because our objective is to separate those that do contain curtain inside them from those that don't. So if I do this, I get answers to the question, does this name contain the word curtain? As you can see, this first one doesn't, so we have false, and those two do have curtain, and the fourth also has curtain. So after we do this, we have to filter, and we need to filter who, not the types, not the names, but the elements. So we go for the elements and we filter using this question and answer here, so that we separate. And in the in, we will have those that have curtain, those that do have curtain in their type's name, and below we have those that don't. So we separate those that don't have curtain in their names, in their type names, in the out. So from now on, we are going to be working just from the out, because these are the walls that are interesting for us. These are the walls from which we want to find the center of gravity. So here I have 3 walls that are curtain walls, and the others below, we need the center of gravity of those walls. Great, so what was the next step? I'm checking the next step here. We already have the normal walls, so now we need their volume and centroid right here. Great, so how do we do that? How do we get the volume and center? First step is to get something from which we can get the volume. And what is that? We need a cuboid. Okay, so from this cuboid, we can have its length, width, and height. And length per width per height, that equals volume. So we are hoping to achieve the volume, if per V per C, we are hoping to achieve the volume of these walls, of the walls that are not curtain walls. So in order to do that, I need the bounding box of each and every wall. Now, I'm going to get the bounding box with this element.geometry. This one will give me the geometry, and I will be able to see the geometry in my Dynamo right here. I can see all the geometry. Great. So here I have all the geometry of these ones, and then I'm finding the geometry bounding box by minimum volume. Now this bounding box is transparent, this is air, but it is super useful in order to make the geometry more simple. Made it just so that we have a cuboid of air. So from here we can click run, and there we go. There we have all this. Now, in this one that you can see with the roof, this isn't going to do well because I'm assuming here that I'm working with rectangular surfaces. So this may not get the result that we expect. Okay, but here I do have the volume. Here I do have the volume of these walls. And I also needed the centroid. So if I go for centroid, here I can go ahead and click and have my solid centroid right here. So these are both the volume and the centroid of each and every wall that is not a curtain wall. So here I have the volume, and on top I have the centroid. Now what else was needed? So I needed to split the walls up between those that have hosted elements and those that do. So how am I going to find out whether these walls do have hosted elements or not? Let's see whether I have here get hosted elements, which I do have. And I'm going to be asking the walls here, and I'm going to be telling this node that yes, I do want to include openings, because some of the elements hosted in the walls may be openings, others may be walls or even windows. So let's include that. And if I click run here, you can see that many of these walls don't have any hosted elements, which does make sense because this doesn't either. Yes, it does make sense. Now I want to split these walls up between those that do have hosted elements and those that don't. So I'm going to be using the fact that those walls that do not have any hosted elements give me an empty list. So let's ask this list whether they are empty. And if I click run, I'm getting true in those lists which don't have any hosted elements, because those are the empty ones. So from here, I can filter again. Here is how I'm going to filter, and I'm going to filter out the walls. Now, right here, I'm separating those with hosted elements that are going to be remaining on the out, and those that don't have any, and I'm filtering it right here. Okay, so for those walls that do not have any hosted elements, I could already be using the centroid as the place in which to put the center of gravity, which I'm going to be including as a family. So I'm going to use this same filter right here with the volume and right here with the centroids. So that right here with the volume and right here with the centroids. Why is that? So that I may have also the center points, the centroids, as well as the volumes separated by those that do have hosted elements and those that don't. Remember, I have in the upper part, in the in, I have the information from those walls with no hosted elements. So I have here the volume from the walls with no hosted elements, and below I have the volume from the walls with hosted elements. And up here, remember that I got the centroid before, I have the centroid. So for those walls that do not have any hosted elements, I could already be using this. So I'm going to be doing that, and I'm introducing a family by point for that. Family instance by point. My points are these ones, because I don't have to take into account any wall, any opening, or any door. They simply don't have it. So there we go. This is how we insert a new family. And the family type that I want to insert here, family types, it's called R25 little ball. And if I click run, you can see I already have here, curious. These ones have appeared right on those that do have windows. Why is that? Because I decided to pick centroid from the walls with hosted elements. No, it's the other way around. So right there. Okay, so now you can see here that they are right in the center of gravity, which is right, the centroid, because they don't have any openings. So this is correct. So here I'm inserting the family in the center of gravity of those elements with no openings, no doors, no windows. But I'm missing something. I'm missing the main aim of this exercise. Because obviously you don't need me in order to get the centroid of a perfectly symmetrical rectangle, do you? You need me in order to get the center of gravity of those with openings. And that is exactly what I'm going to do. So from here, where I do have the walls with hosted elements, which are 2, I'm going to repeat the action and get the hosted elements, but only of those that do have hosted elements. So if I do this, I get that the first wall has 1 window and the second one has 2. And now from these windows, I need both the centroid and the volume, which is something that we did before somehow. So I'm going to select this group, copy it, but instead of referring to the walls, I'm going to be getting the volume of each and every hosted element in the walls with hosted elements. Now, here we may encounter some trouble, but let's try it like this. So I click run, and as you can see, I here have many solids conforming an only window, but as we pick bounding box by minimum volume, they get reduced. Each one is bounding box gets every solid that the window contains. And after that, we are transforming this to cuboid, and here we do have the volume. Great! And what else? Oh, we do need also the centroid. So the centroid of these cuboids are the centroids of the windows. Now, there's just one little step left, which is to combine the centroids of the walls and its windows in order to get the combined centroid of the complete figure. So this I did with a little help from my friend ChatGPT. This is the formula for the compound centroid, and we need to use it in combination with Python in order to achieve the desired result. Now this, I didn't get this on the first prompt or the second or even the fifth, but with a little knowledge of Python and geometry, maths and ChatGPT, you can get this final result that I'm going to show to you. So this is in Spanish. So here my inputs will be the wall points, which means the centroids, wall volumes that we already calculated before, the void points from each and every window, wall, open that we have inside the wall, and the void volumes. So here we have a definition to extract the data when we reach a point. Here we have a definition to extract the number of that data. And here we are combining everything into list, extracting the points and the numbers for the points and the volumes. Here we have to watch out for the levels of the list that do come in, because a wall may have more than 1 or 2 or 3 elements inside it. So we have to take that into account. And after that, we compute the summation of the wall volumes and centroids and subtract the contribution of each and every member inserted inside them. And if we do that, we get the adjusted centroids. Now I'm going to copy this and include it here and parcel it a bit below this document, instance, current document, and all that. So here I need the wall points of each and every wall. No, not of each and every wall, only those that have hosted elements, so these ones. Then the volume, which is right here, and then the points of the voids that are right here, and their volumes. And if I save and run, and here I have 2 points. Why is that? Because beforehand I only had 2 walls, so it does make sense. So after this, I'm only left to include these points with their little ball. And if I click run, let's see whether this does make sense. Okay, run. It does make sense, because here, for instance, we do have it on the right side of these windows. It wouldn't make sense to have it here on half of the gap, and here it's moved a little more to the right than if it was just in the center. Why? Because it's compensating for these 2 little legs, okay, on top and bottom. So that's all for today's video. I really hope you have found this useful. Now, I'm sure that after this definition, you really don't want to miss anything more out. So next week, 27th of March at 6 p.m, I'm hosting a masterclass. And if you want to attend to that masterclass, I'm leaving you here a QR code so that you may join. And of course, you can subscribe to the channel. See you on the next video. Bye bye.